for H parameters. This is a very important discussion in that case if we are doing it for the very first time. Okay. Let us start with the common emitter configuration. Are you able to see the screen?
Yes, sir.
Yes, sir.
So the very first thing is the common emitter configuration, H parameters. Okay. So we already have the circuit with us, the configuration with us. So I'll draw it again. So since you're talking about common emitter terminal is going to be common. This is your base. This is the collector emitter. Naturally, the output is VCE. Okay. For the timing, we call this plus minus. We have the collector current IC. We have the base current IB. This is your VBE. Now remember that we are talking about the H parameters, means we are see, this is basically is nothing but the two-port network which we have already seen. So we can now represent this as the H parameter.
Excuse me, sir.
Yes. Yeah, go on.
Sir, output मतलब VCE output terminal पे minus plus हो गए ना? Inverted.
एक minute. When we are talking about the H parameters and when we are talking about the two-port network, if you remember that we had taken the signals, we had taken this VCE, we had taken the V1, I1, V2 and I2, and we had taken I2 as going into the network. Do you remember that? So if I2 is going inside, this has to be positive. Okay. Later on, we will see that this VCE becomes negative. If it is having a different polarity, it will simply become negative. That's all. But in order to make sure, do you remember that two-port network?
Okay.
So if we identify this as a two-port network, this was the common terminal. And we said that this was a two-port network. Let us say this is a BJT now. So then we had said this was I1, this was I2, and this was plus minus V1, this was plus minus V2. So what I'm doing is I'm trying to simply keep the same polarities here. Excuse me, same polarities here, and then my V2 will be minus VC. Doesn't matter. It's just the change of polarity will be there. If that turns out to be like that. Are you getting this? Yes? Yes or no?
Yes, sir.
Yes, sir.
Okay. So now we will convert this into its H parameter equivalent, H parameter model. So again, in terms of the two-port network, this becomes it can be represented as a voltage source and a current source. Look at the direction of the current flow. So this was your emitter. This is your base, and this is the collector. Okay. Then we will say that this was IB. This is IC. Here we have VBE. Okay. And here we have VCE. This is your 1 by HOE. This is HFE into IB. This is HRE into VCE. This is called as HIE. So we are representing the transistor, bipolar junction transistor, in terms of the H parameters. We have already seen the H parameters from the perspective of a two-port network. So just translating it, what we get is VBE. Do you remember those two equations which we started off with? It will become HIE into IB plus HRE into VCE. And the second equation, IC, happens to be HFE into IB plus HOE into VCE. Just recollect what we had done in case of the two-port networks. Okay, I think in one of the lectures I have shown you the two-port networks. I don't exactly remember which one. This is biasing, so maybe in some earlier lectures. Anyway, it doesn't matter at this point of time. Okay, so if you have not done that, let this be for the first time. So this is the common emitter configuration, H parameter, or in simple plain words, your BJT is modeled in terms of a two-port networks where the parameters are these HIE, HRE, HFE, and HOE. Okay, where HIE is nothing but delta VBE by delta IB when we have VCE constant. Now you'll be surprised maybe for the first time if you look at such a kind of an equation, why we are having this kind of. So basically when I talk about HIE, HRE, HFE, and mute your microphones, please. Maybe I have to do it here. Okay, so when I have, how do I get this? How do I get this value? Look at this equation, the very first equation. Now, if I apply a small change to all this VBE, HI doesn't change, it is a constant. This will be delta IB. And of course, I'm maintaining VCE to be constant. So delta VCE will be 0. So this entire term goes off. And then I can say that HIE is nothing but change in VBE divided by change in IB. Now, please remember that we are talking about the AC here. Okay. So that is the reason why I am taking this as a small lowercase be, lowercase b here. So VBE, IB are, these are the signals, change in the signals, maybe the change in the signal current and the signal voltage. All right. So that is how I get this HI. Please remember this very carefully. Now next, if I want to find out HRE, what should be the condition? So what will be the equation for that? HRE will be delta VBE divided by delta VCE
Delta
when
VCE.
I keep IB constant. We have already seen this from a different perspective. This was, if you remember that, this was H11, this was H12. Right?
Yes, sir. Hmm.
So just correlate that with this and you will sail through very easy. Then using the second equation, I get HFE as delta IC by delta IB.
IB.
Yes, when I keep VCE constant.
VCE constant.
Similarly, I can have HOE
HOE.
as delta IC
The
over.
IC by delta
Yes,
VCE.
very good, very good, very good. When I
And
keep
keeping I constant.
IB constant. So these parameters I get when I, so in fact, what is this interpretation? The interpretation is that I can replace the transistor with its H parameter model in simple plain words. Okay, so that is what we get. Now this HFE, we have seen a different variety of this as HFE. It's simply as IC over IB. Okay, when your VCE was constant. See the change? See the difference here? Do you see the difference here? So this actually is called as beta AC and this is called as beta DC.
DC.
And this beta DC is what we have used in the stability and all that designs. All right, because we were dealing with the DC levels over there. But when we come to amplification, we're supposed to find out, we are supposed to use this beta AC. Or in simple plain words, we'll not drop the use of this beta AC and use only this HFE. It is nothing but beta AC. Are you getting this?
Yes, sir.
Okay. Now when I
Yes, sir.
talk about the second configuration, and that is the common collector configuration, let us say. Configuration H parameter model. So let me first of all draw the circuit diagram. Drawn in a slightly different way, but you can correlate those things very easily. So again, this is the base, this is the collector. So collector is common now. So this is collector.
Yes, sir.
This is your emitter. I've drawn it in a slightly different way, nothing great. So again, in terms of the two-port network. This is IB. This is your VBC. Again with this polarity. Now this is IE. Remember the output current in common collector is IE, emitter current. And this is VEC. Again, you will ask me the question. You will ask me the question. The arrow for transistor is like this. So how are you? Why are you drawing it in this way, this direction? But what will be the interpretation? This IE will turn out to be negative. That's all.
Yes.
Okay. Oh,
Yes,
all right.
sir.
So this is the common collector configuration, and we are drawing the model, H parameter model. Again, you'll see the pattern over here, and that is we are always going to use a voltage source in series with a resistor, a current source in parallel with a resistor. This always is going to be the picture. So better remember this nicely. So similarly here I have, this is the base, this is the emitter, and this point is the collector. Here I have the current flowing here is IB, current flowing here is IE, right? Then I have the input as VBC, output as VEC. VEC. Okay. Now the current flow direction is again the same like this. Here in this case, this will be HIC. Okay. This will be HRC. VEC. This will be what? Anyone? What will be this? Current source. What will be the current source?
HFC.
HFC.
HFC into
HFC
IB.
into IB.
IB.
What will be this? 1 by?
HOC.
HOC.
Correct. Now you're getting the
Okay.
feeler. Good. So this is the H parameter equivalent model for transistor in common collector configuration. Okay. Now we'll write down the equations again. So VB, please remember that VBC will be equal to now what? HIC into IB plus HRC into VEC. Similarly, IE will be, sorry, it should not be capital. IE will be equal to HFC into IB plus HOE into VEC. You're getting this? So from,
HOC होगा ना.
oh sorry, HOC. Correct, you're right. HOC into VEC. All right. Again, you can find out what is the value of HIC, HRE, HFC, and HOC, just like what we did in case of common emitter. ठीक है ना? Third one we will have as the common base configuration H parameters model. So I'll start drawing it again. This is your emitter. This is your collector. This is the base, because base is common here. So we have the current flowing here as IB. Input current is IE. Output current is IC. Input voltage is VEB. Output voltage is VCB. Okay. Let us see the H parameter equivalent. It is very easy if you see the patterns. Same thing. This should be a standard template like thing. Okay, now you're going to tell me this is the voltage source. Again, this is the current source. Okay, so this will be your emitter. This is base. This is base, and this is collector. You have the current flowing as IE, with the current flowing as IC. All right. This will be your VEB at the output side. You have the voltage VCB. Now you have to tell me what will be this parameter. Yes.
HIB.
Very good.
HIB.
What about this guy?
HRBBC.
HRB
HRB.
VCB. All right.
Yes, sir.
What about this fellow?
HFB.
HFB.
HFB
IE.
IE. Correct. What about this? 1 by
1 upon HOB.
HOB. So you have now understood the pattern, at least. Okay. So now we can again write down the equations just like what we did last for the last configuration. VEB will be HIB into
Into IE.
plus HRB
HRB
into
into ECB.
VCB. This is one equation. Similarly, IE will be equal to, sorry,
IC equals to
IC equal to HFB into IE plus HOB into VC. See, it is easy to remember. All these are same here. All right. The first equation is the input voltage V1. Second equation deals with I2. That is the output current. So these are the two equations or the two functions which are dependent on IE. Do you remember that? So this was your IE, what is IE? It is I1. VCB is what? V2.
V2.
Okay. So we had said earlier that V1 is a function of I1 and V2. Similarly, I2 is a function of the same quantities. Remember this? That is what we have established here. So now once we are ready with the H parameters, let us see the approximate conversion of each parameter. Now the manufacturers won't give you all these parameters. They will give maybe um, only for common emitter, and you can derive those from the other parameters. Okay. So we will see the approximate conversion and the typical values. I think we have done this. There was a table, no? Anyway, we'll do it again. Doesn't matter. Let this be. So we have the approximate conversion formula for H parameters. So I have a table here, so I have to draw it. Maybe more space is required. Okay, so we have the symbol. This is for common emitter. This is for common collector. And this is for common base. So the symbol is HIE. Typical value of HIE for common emitter is 1.1 kilo ohms. Okay. Now, if I want to equate that, convert it for common collector, it is exactly the same. Whereas for common base, I have to have this formula HIB divided by 1 plus HFB. So these are the conversions. So given H parameters, you can convert into H parameter for common emitter, you can convert into common collector or common base, and so on and so on. Okay. The next one is HRE. HRE for common emitter is of the range of order of 2.5 into 10 to the power minus 4. What are the units? What are the units?
Ohm obviously.
Yes. What is HRE?
किलो ohms.
HRE देखो क्या है? HRE का रेशियो देखो
Delta
क्या है?
V by
So it is a ratio of voltage over voltage. So will it have any unit?
no.
No, sir.
So there are no units. Okay. So there are no units here. If I want to convert it for common collector, it is 1 minus HRC. In case of common base, it happens to be HIB into HOB divided by 1 plus HFB minus HRB. Don't get overwhelmed by these things. I'm just showing you that you can convert from one to the other. No need of mugging up these equations. HFE. The typical value of HFE we have seen, we have used 50 most of the times. Maybe, of course, changes from transistor to transistor. In case of common collector, it is 1 plus HFC. In case of common base, this happens to be minus HFB divided by 1 plus HFB. What about the fourth parameter, HOE? Okay, this is, what will be the units of HOE? What is the ratio of it basically? How do we find out HOE? It is the
It's
ratio of
current by
delta
voltage.
delta.
Delta IC
I
upon delta VCE.
Yes. So it is what? What are the units?
So Siemens में होगा.
Yes, correct. So typical value is 25 microsiemens. This is same. Here it is HOB divided by 1 plus HOB. Okay, this is for common. I mean, this is the first. So next is HIB. Now, in terms of H parameters in common emitter configuration, this happens to be HIE divided by 1 plus HFE. Here in this case, it is minus HIC divided by HFC. This is common base, so we have typical value of 21.6. What is the unit?
Ohms.
Very good. In fact, in the first assignment itself, I have told you to calculate the input resistance, input impedance, output impedance. These values should be very, very close to that. Okay, because HIB is nothing but input impedance in common base configuration. So just verify that. HRB, here you have some hefty equation, HIE into HOE divided by 1 plus HFE minus HRE. Again, don't be afraid of these equations. This is HRC minus H. These are simply conversion formulae. Okay, so for typical value of HRB is 2.9 into 10 to the power minus 4. HFB, it is minus HFE divided by 1 plus HFE. Here it is minus 1 plus HFE. Sorry. HFC divided by HFC. And HFB for common base, typical value is minus 0.98. HOB is HOE divided by 1 plus HFE. For common collector, it is minus HOC by HFC. Typical value is 0.49 microsiemens. This was for common base. Next is HIC. It is same as HIE. Typical value is 1.1 kilo ohm. In this case, the conversion will be HIB divided by 1 plus HFB. Then we have HRC. 1 minus HRE. Typical value is 1. And for here also you have 1. HFC, this will be minus 1 plus HFP minus 51 minus 1 divided by 1 plus HFB. Then we have HOC, same as HOE here. Typical value is 25 microsiemens, typical value. And here we have HOB divided by 1 plus HFB. So with that we see the conversion that is possible.
सर
Yes.
सर प्लीज HOE था जो, उसके लिए कॉमन बेस वाले का एक बार आप ऊपर स्लाइड करके टेबल चेक करवा सकते हैं?
ओके, ठीक है।
सर HOE के लिए
हाँ,
सर वो डिनोमिनेटर में 1 प्लस HFB होगा या फिर 1 प्लस HOB होगा?
HOB. दिस इज फॉर
Okay,
HOE,
sir.
नो? डिनोमिनेटर
Yes.
में, इसके डिनोमिनेटर में
HFB होगा ना, 1 प्लस
हाँ,
HFB.
it should be HFB, correct.
हाँ.
Correct. HOB or 1 plus HFB. This should be HFB. Correct. Very good. Okay. That's right. ठीक है.
Yes, sir.
All right. So with that, we have seen the H parameters, the typical values. Again, we go back to our common emitter amplifier now and try to analyze the circuit which we had started off with yesterday. This one. Okay. So what we have done here is we have simply substituted the BJT with its H parameter equivalent model. We are going to see the derivation for each of these circuits. Again, look at the big picture. What I am interested in is the input impedance, the output impedance, the voltage gain, the current gain, and if possible, the power gain. Okay. So this is what we are interested in deriving for each of these circuits. Okay. Let us start with input impedance for bypassed RE circuit. Okay. So just, okay, what I'll do is I'll copy this figure instead of drawing this. Okay, so that we can start with the derivation. We will be required to go back to the circuit again. So the very first A is the input impedance. All right. Again, you may have to refer back to the table many times when I say some things. So how do you find out the input impedance? Basically, input impedance is what ZB for the device. Please remember that we are having two flavors of input impedances, output impedances, right? One is the device input impedance, the one which is shown here, and the one is the circuit input impedance, the one that is shown here. Similarly, output impedance for the device will be this, output impedance for the circuit will be this. So we'll first of all start with finding out these values. Okay, so what do you see here? What will the signal, if I inject a signal here somewhere between these 2 points, what is the resistance that is seen? What is the impedance that is seen? Yes, looking into these terminals.
Sir, HIE plus HRE BC upon IB.
Please remember that HRE, what is the value of HRE? Go back to the table and see. Where is
Sir,
that?
HRE for common emitter now.
Yes, what is the value?
Sir, it is 2.5 into 10 to the power minus 4.
-4 or -5, isn't it? -4. So
Minus 4.
it is a very small value. It simply means that a very small fraction of VCE is available over here, and this HRC value is very, very small. So I can simply neglect it. Okay. So what I can do is I can say that ZB is HIE itself, but we know that because HRE is a small quantity. You're getting this? We are able to ignore the effect of this HRE into VCE because HRE itself is a very small quantity. So input impedance, the device input impedance is nearly equal to HIE. This is very, very interesting. Okay? You're getting this? Simple. Very simple.
Yes, sir.
But this is not the picture with the one which is unbypassed. Now we will have a small one sec. Where is it? Okay. So here the picture is little bit different. See, where is my input impedance now? Between which terminals? If I mark it again here, the device input impedance will be, this will be ZB. Yes, this will be ZI. All right. This will be ZC and this will be ZO. Now between these 2 points, see this point, and this point. Now I am having this additional thing over here in series with HI. You getting this?
Yes, sir.
So even if we ignore this HRE, we see this RE is going to come into picture. So for that, we have to see some derivation. Let us do that. So this was for bypassed RE. Okay. For unbypassed RE, we have to now derive the equation. Okay. So what is a simple way of finding out the input impedance practically? If I want to find out the input impedance, say I'm given a black box like this. Okay. This is your input current I1, input voltage V1. What is the simple way in which I can find the input impedance ZI?
Sir, V1 by I1.
Yes. So you apply a voltage and simply measure the current, isn't it? So ZI will be equal to V1 by I1 simply. In a similar way, we are going to derive the equation wherein I can have input voltage over there and the input current. Simply take the ratio and find out what is the input impedance. All right. So we start with what is the voltage that we are applying here? It is VI. You're getting this?
Yes,
This.
sir.
So we are having VI. So what I will do is, one second. We are, okay, let me copy this thing so that will be easier for you to understand. Okay. Just have a look at this. I'm applying VI. I'm applying this VI here. All right. So what is this VI? If I write an equation, VI is equal to, what is this? This is the base current IB. This VI gets distributed among this resistor and this resistor. So VI is nothing but whatever is the drop across this resistor plus drop across RE. Agreed?
Yes, sir.
Yes, sir.
Okay, so
Yes,
can I
sir.
write it like this? This as IB into HIE
HIT
plus IE into
RE.
RE.
RE. Excellent. Again, we are ignoring,
HRE, VAC.
yes, HRE into VCE. Or output voltage. VC is nothing but the output voltage. Okay. So is this equation clear to all of you? If
Yes.
you are
Yes,
able
sir.
to understand this, then things will be very, very simple. All right. Now it
Yes, sir.
becomes very easy to find out. So what is our big picture? What do we want to do? What is our objective? Our objective is to find out the ratio of
Impedance
VI to IB,
IV.
isn't it? Once we
Yes,
do
sir.
that, we can get an equation for the input impedance over there. So I will simplify this further as IB into HIE. Yes. Is there any doubt?
No, sir.
Is there any doubt? अरे यार बात क्यों कर रहे हो तुम लोग?
पूरा टूट गया था ना घर, उसके बाद इधर रह गया सारे को चल गया।
ये देखो ये क्या कर रहे हैं बात.
म्यूट सर.
उस समय 50,000 का था, उस समय मतलब कम से कम आज से 7-8 साल पहले।
See what people are doing. See what people are doing.
अब 1 लाख
सर आप म्यूट कर दो सबको.
You see how serious people are, and then later on they say that electronics is very difficult. I really can't understand the attitude of the students. You know, I am conducting the lecture from home. To the extent I had a tragedy, family tragedy on Friday. In spite of that, I am conducting the lecture. And students are not serious. All right. This is IB into HIE. plus, we already know what is IE. IE is
IB plus IC
IB plus IC into RE. Now taking out this IB common, this will be HIE plus RE. Can I replace this IC with something?
Yes, sir. Beta into IB.
Beta
Okay,
IB.
drop the use of beta and we will use IC is equal to, yes, HFE times IB,
HFE times IB.
right?
Yes, sir.
Yes, sir.
So can I write it like this? 1 plus HFE. Is it okay?
Yes, sir.
Fine.
Yes, sir.
Now the left hand side I have voltage, right hand side I have a component, current component. So I can simply take the ratio. So input impedance ZI, which is nothing but VI divided by IB, happens to be HIE plus 1 plus HFE into, this is what I get. This is the very first equation that I get for input impedance. Very, very important. So just a brief comparison. If RE is unbypassed, what is the input impedance?
HIE. It was for bypass. Unbypassed.
Sorry,
it
this was not ZI. I'm sorry. See, this is what happens when I get disturbed. Yeah, this is not input impedance for the circuit. This is input impedance for
ZP होगा ना ये.
the device.
Device, yes.
Yes, sir.
This is the input impedance for the device. So look at the comparison. Input impedance for device when it was bypass was only HI, whereas in this case it is HI plus 1 plus HFE. So because
HFE into RE.
because of RE, can we say that the device input impedance has increased? Can I say that?
Yes, sir.
Okay, so we have an increase in the device input impedance. Now what about the circuit input impedance?
So we'll use R1 and R2 there.
Yes, R1 and R2 will come into picture. So what we have here is something like this again. So I'm just, so this will be your ZB, and then you have these two resistors over here, R1 and R2, and now the input circuit input impedance is ZI. So this we have calculated already as ZB. So what do you think will be the circuit input impedance ZI finally? This guy in parallel with this guy in parallel with this guy. That's it.
ZB.
It will be R1 parallel
In parallel with R2. Parallel with Z.
With Z.
That is it. So that is how you can derive the equation for input impedance of the circuit employing common emitter configuration. Please remember that these are all related to AC only. ठीक है ना? So that is it. Let us quickly see before time is over for us. Let us quickly see the output impedance. ZO. So looking into the collector terminal or collector to emitter terminal in both the situations. See, ZO is looking into the collector collector and emitter terminals. Okay. Here in this case, similarly here in this case. What do I have? First of all, again I have to figure out the device output impedance, isn't it? So the device output impedance will be ZC. So what do I have ZC as? If I look into the collector and emitter terminals, for example here, what do I see? 1 by HOE.
HOE.
Yes, 1 by HOE. Please remember it is 1 by HOE. It is admittance. So ZC is what? Is nothing but 1 by HOE. Can someone find out quickly what is the value of HOE? Typical value of HOE? What is the typical value of HOE?
25 microsiemens.
Okay. So it is 25 microsiemens. So it is 1 over 25 microsiemens. What does this amount to? This will be a large value. You getting it? This will be a large value. To be more precise, I think it will be 40 kilo ohms.
Yes, sir. 40 kilo ohm.
40 kilo ohms is a large value. Okay, so ZC is nearly a high value resistor, which is 40 kilo ohms. Even if I have for unbypassed RE, you may see that you may wonder that it will be this HI 1 by HOE plus RE. That is the value of resistance that you see, no?
Yes, sir.
Yes,
Again, typical values of RE are in the range of 1 to 2 kilo ohms. So 1 to 2 kilo ohms in series with a huge value of 40 kilo ohms. So I can say that this is nearly 40 kilo ohms.
Yes, sir.
So in both the cases, ZC is going to be 1 by HOE. What about ZO? So again,
will be in parallel with RC.
excellent. So this will be your ZC and I'm having this as RC. So what will be the effective circuit input output impedance? This will be
ZC RC upon ZC plus RC.
simply ZC parallel with RC. We already know that this is 1 by HOE. So this will be 1 by HOE in parallel with RC. This is the equation for output impedance of the circuit. All right. Clear to all of you?
Yes, sir.
Please practice this derivation. Otherwise, you will not be able to remember it later on. Okay, I think we have already run out of time. So I will extend the dates for your submission because I'm not in a position to assess your assignments at this point. Okay, are there any doubts, any questions till whatever we have done?
No, sir.
Okay.
No, sir.
I think only a few people are really serious about this subject. Anyways, so we will stop. We'll continue with the derivation tomorrow. Okay. So thank you.
Okay.
Thank you.
Thank you.
Thank you, sir.